Now, I would like to discuss the inverse Laplace transform. The inverse of a Laplace transform is written as uh, the Laplace inverse of some function f of s, and it should return a function in time. So this is generally performed through inspection. Like we know the Laplace transform of uh, t is equal to 1 over s squared. So in inverse operation, if we encounter 1 over x squared, then its Laplace inverse would be written as t. So there is that is the standard practice. Similarly, uh, Laplace inverse of 1 over s minus a. So we have to look for a function whose Laplace transform is 1 over s minus a. So we know that is such function is e raised to the power at. So that is the way to do the Laplace inverse transformation. So here from the reference book by Professor Zil, we have the transform, and then likewise in the inverse operation, this function, uh, its inverse is computed by inspection, is calculated, or analytical expression is returned by inspection. Okay. So we have the example 1 over s squared and 1 over s squared plus 7. So let's let's calculate that. Example 1, a part. So f of s is equal to 1 over s raised to the power 5. So we know the forward property, Laplace of t raised to the power n is n factorial over, it's n factorial over s raised to the power n plus 1. So for this one, before doing that, uh, I would multiply 4 factorial and divide it by 4 factorial and s raised to the power 5. This is the definition of f of s. So then f of t would be Laplace inverse of 4 factorial over 4 factorial s raised to the power 5. And then with the complete structure, it would become t raised to the power 4. For the b part, uh, f of s is equal to 1 over s squared plus 7. So this structure seems to be the similar to the structure of Laplace of cos of at. So we could recall that it was a over s squared plus a squared. So in the structure, I can multiply the square root of 7 and square root of 7 divided, and then s squared plus the square root of 7, and then with the inverse transformation of 7, square root of 7 times s squared plus 7 So by comparing the structure with the forward Laplace calculation, so we can have this one as the cos of square root of 7 times t. So let's see what's there in the next example. Okay. Uh, so, well, I made a mistake. 1 over s squared plus a squared. So this was the, with the constant, it was sine of 70. Okay. For sine of kt, there is the constant. Yeah. So my mistake. My mistake. So uh, I forgot that structure. So, okay. So it requires practice. Sine of at, its Laplace transform is this one. So and therefore this must be corrected as sine of this function. Okay. Then this is the problem. Minus 2s plus 6 and then s squared plus 4. So minus 2s plus 6. Example 2. F of s is minus 2 times s plus 6 and divided by s squared plus 4. So the expression can be simplified. So 2 times s over s squared plus 4 plus 6 over s squared plus 4. So the structures are similar to the sine and cosine functions. So therefore, f of t, Laplace inverse of f s is equal to minus 2 times Laplace of s over s squared plus 4 plus 3 times 2 and Laplace inverse of s squared plus 4. So with these familiar structures, it is minus 2 times s over s squared plus 4. Now it is cos of 2 times t plus 3 can be taken out of Laplace inverse transform. And then this is the sine of 2t. Yeah. I have to move forward. Okay. So the next example, example 3, contains a um, structure which is numerator and denominator. So we have s squared plus 6s plus 9 over s minus 1, s minus 2, and s plus 4. So the partial fractions can be developed. So with the partial fractions, a over s minus 1, B over S minus 2, and C over S plus 4. So these structures are familiar structures for computing the Laplace transform, uh, which gives to E functions. Example 3. F of S is equal to S squared plus 6x plus 9 and over S minus 1, S minus 2, and S plus 4. Yeah. So then we can write this expression in conformance with the partial fraction structure. S minus A, S minus 2, and S plus 4 is equal to a constant A over S minus 1 plus B over S minus 2 and plus C over S plus 4. And then therefore the function in time will be with Laplace inverse of the f of s expression, and therefore it will be uh, calculated with the simple property. So without calculating a, b, c values, uh, I can write it is e raised to the power t plus b times it is e raised to the power 2t and plus c times e raised to the power minus 4t. I hope the expression for the process for calculating the partial fraction is known to the students. So that is left as an assignment. Next. Okay. Let's see what next we have. So the partial fraction calculation is a bit involved. However, the functions e raised to the power t, e raised to the power 2t, and e raised to the power minus 4t, that has been correctly calculated. Now the final link with the differential equations, it is with the transforms of derivatives. So transforms of derivatives. So this will enable us to apply Laplace transform for the solution of differential equations. So as a matter of notation, defining a notation, so Laplace transform of y, I will represent that one with capital Y uh, as a function of s. So we would like to first generate the expression for Laplace transform of y prime. So this is the first definition. So because in our differential equation, we will encounter y prime in the first order differential equations. So we will evaluate it with the original expression of Laplace transform, the integral. So 0 to infinity, it is with y prime e raised to the power minus st and dt. So it will be evaluated as the first function as e raised to the power minus st, and the second function integrated. So it is y prime dt from 0 to infinity minus the derivative of the first function, and therefore it is e raised to the power minus st times minus s, and the integral of the function. So it will be a function of y of t dt. Now it is e raised to the power minus st, and when it is evaluated, it will be the function of y, and it should be evaluated over limits from 0 to infinity. This would become plus and s, and from 0 to infinity e raised to the power minus st and y dt. So this is with then limits of limit t goes to infinity for e raised to the power minus st y of t minus uh, e raised to the power 0 and y of 0. This is very interesting thing which is appearing over here, that e raised power 0 is 0 and y of 0. This, in the context of differential equations, this is the initial condition. So while evaluating the Laplace transform of derivative, the initial conditions naturally appear in the definition of the Laplace transform of derivative. Okay, plus this s is here, and then this integral, it is the Laplace transform of y. So we are almost done. Uh, for this limit, we can notice that y of t is considered to be a continuous function, which means it is going to have some finite value at t goes to infinity, and e raised to the power minus infinity, it is going to vanish this month. So finally, we will get the last term, s times the Laplace of y, which I write with the other notation, minus y of 0. So this is the definition of Laplace transform of y prime. On similar lines, uh, if I would like to attempt the Laplace transform of y double prime, so it will be uh, s times the Laplace transform of y prime minus y prime of 0. So just like the expression I have evaluated for Laplace transform of y prime, so it was simplified to s times Laplace of y minus y of 0. So I have written that on the same analogy, and then I can use the expression for Laplace transform of y prime So it is s times y of s minus y of 0 minus y prime of 0. So it is then s squared Laplace of y minus s times y of 0 minus y prime of 0. So we can inspect a pattern in this expression. So similarly, Laplace transform of y triple prime, it can be written as s cube Laplace of y function minus s squared y of 0 minus s times y prime of 0 and minus y double prime of 0. So all the initial conditions are naturally appearing in the expression of Laplace of derivatives. So we have learned how to calculate the Laplace transform of derivative functions and also the Laplace transform of sinusoidal functions, hyperbolic functions, exponential functions, and the piecewise functions. So this is all the basis for solving the differential equations. So let's attempt an example. So example 1. So I use the simple case of radioactive decay, which is one of my favorites, radioactive decay. So it's a first order differential equation. It's written as dy dt equals the constant for decay minus lambda y. And let's assume that y of 0 is equal to, okay, the general binomial. So with the differential equation, we take the Laplace transform on both sides. So it will be Laplace transform of y prime equals minus lambda Laplace transform of y. So this will be s times y of s minus y of 0, the initial condition, and it is minus lambda times the Laplace transform of y. So we have s plus lambda times the Laplace transform, and it is equal to the initial condition. So I have made some arrangement of the equation. So y of s, it becomes y naught over s plus lambda. So having the complete equation transformed by Laplace um, transformation. Okay, so we can generate the solution y of t by taking inverse transform. So inverse transform is equal to the inverse transform of then the right hand side y naught over s plus lambda. So y of t expression, uh, it is then simply the property 1 over s plus lambda. So it is e raised power minus lambda t. So that's how we use the Laplace transform for solving the differential equations. Let's solve another example. From the book. The transformation of derivatives. We did that. The recipe has been shown. There is example 4. And then example 5. It's a second order differential equation. So, okay. Uh, let's attempt this one. Y double prime minus 3y prime plus 2y is equal to e raised power minus t. Mhm. So the problem is y double prime minus 3y prime plus 2y equals e raised power minus 4t. So let's solve it by Laplace transform. So I require the Laplace transform of the equation. So Laplace transform of y double prime minus 3 times Laplace of y prime plus 2 times Laplace of y and the Laplace transform of e raised power minus 4t. So the mixture of functions. So y double prime, it is Laplace transform of y double prime. So it is s squared y of s minus s time y of 0, the initial condition, minus the second initial condition, y prime of 0, minus 3 times the Laplace transform of y. Okay, it is s y of s minus y of 0 plus 2 times y of s. And on the right hand side, it is 1 over s plus 4. So then it is to be carefully simplified. So if I pick up the coefficient of y of s, it is s squared. Then from here it is minus 3 times s, and then it is 2 times plus 2 times y of s. Okay, the terms has been collected. Minus s y of 0. Y of 0 is 1. So it is then s. Y prime of 0 is 5. So it is minus 5. And then minus 3 times y of 0 is 1. So 1 is equal to 1 over s plus 4. So then y of s, it will be equal to 1 over s plus 4. And over here it will be s plus 8, 3 and 5. We make 8, 5 and 3. Okay, well, this should be plus and so, well, I noticed that this minus, this should be plus. So therefore, minus 2, and it will become here plus 2. And the rest of the expression will become a divisor, s squared minus 3s plus 2. And over here it is s squared minus 3s plus 2. So the differential equation has been transformed to an algebraic equation, and that's the promise of Laplace transform. So finally, the inverse transformation would lead to the expression in the t variable as independent. So y of t will be the final solution. So the job is to get the Laplace transform of the inverse transform of the function f of s and the inverse transform of the function g. So in both the Laplace transforms, inverse transforms, the partial fractions are required. So the rest of the task is being left as an exercise for the students. And they can also refer and review their solution from the textbook, as it is one of the examples from the text by Professor Z.